hi everyone. Welcome to, again, Math 2414 review session. And this week we're going to be doing long division and, let's see. It's mainly long division and partial fraction decomposition. We're also going to be doing some review on like trig integrals that we did last week. Cool deal. So we start out with long division. Just show of hands, like, are most people still comfortable doing polynomial long division? Like, are we cool with that from previous classes? Anyone feel like they kind of need a review on it? Okay, cool. So we'll go through it then. Okay, so polynomial long division is just the way we can reduce down ratios of polynomials. Given you're in the situation where we're dividing a higher degree polynomial by a lower degree polynomial. Right, so for example, you couldn't use, you have like x squared plus 4 over x cubed plus 2x. You couldn't use polynomial long division here because we see the lower degree is higher than the upper degree. That would not work. So just demonstrating the process for this example right here, x cubed minus x squared plus 4x minus 4, all divided by x minus 1. We should start out by writing it as, in this format, denominator, roof, numerator. So let's all get that down. The next step after that is we're going to take, if you can see right here, what's the leading term of the numerator? X cubed. And what's the leading term of the denominator? X. So what we're going to do is we're going to divide the leading term of the numerator by the denominator's term and put on top of the roof. So in our example, what's x cubed divided by x? Right, so we would have x minus 1 square root x cubed minus x squared plus 4x minus 4. And then since x squared is the division, we write x squared on top. After that, now we multiply this term we got up here by the denominator. And subtract from numerator. So what is x squared times x minus 1?
X cubed minus x squared.
Right, so squared x minus 1. So if I multiply these two together, we would get x cubed minus x squared. So I subtract numerator, or this, from the numerator. You can see will lead to cancellation and cancellation. Cool. And then finally, division over these. And from here, we're just going to keep repeating that process until we factor the numerator all the way down. So now that our new leading term is 4x, what is this leading term divided by the denominator's leading term?
4.
4. So imagine 4. Sorry, 0, plus 4x minus 4. So good, it is. Yeah. 4, so we multiply these out and we get 4x minus 4, which cancels. And so we have our answer is x cubed minus x squared plus 4x minus 4 all over x minus 1 equals this, x squared plus 4. All right, so far so good?
Question, so with the work you did under step 3,
Yeah.
so you're multiplying the x squared by x and the minus 1, right?
Right.
Shouldn't you have to distribute the negative within it?
Which
She got,
negative? When I multiply x squared by x minus 1?
never mind.
And then I just subtract that term from the. Okay, cool. You all good? So, it's an integration class. Let's do. So the reason we're learning about long division is that it has applications when we're doing integrals. So for one example, let's say we have integral of x cubed plus 2x minus 6x minus 4 over x minus 4. Okay, so just to double check it meets our conditions, is the numerator's power greater than the denominator's power? Or degree, I should say. Right, good. So we can do long division upon it. So step 1, let's write it out as a roofed form. One thing you can do here is you notice it skips from, the x cubed term to just the x term. People like to kind of line them up by, it's like degree of the term. So if there's no x squareds in here, sometimes you see people write 0, like a 0x squared line right here, just to compensate for it. Oh, sorry, I miswrote the That is kind of a weird example. X minus 4, okay. So first step, what's the leading term of the numerator divided by the leading term of the denominator? X squared. So x squared is that term, and when I multiply this by this, I get x cubed minus 4x squared. Okay, I subtract these two polynomials. Let's see, x cubed minus x cubed is 0. And what is 2x squared minus negative 4x squared?
Negative 2x.
Hmm?
Negative 2x. No, it'll be
6x squared, right? And then break this down. Okay, what's our new leading term?
6x.
Right, so this leading term divided by that leading term is, right, 6x. And so I multiply these out and I get 6x squared minus 24x. Do the subtraction one more time, and we get 0 plus 30x minus 4. And finally, this leading term is 30x, so divided by x just becomes 30. And let's see, multiply these back together. 30x minus 120.
Question.
Hmm?
So, in like the original integral, you put minus 6x?
Oh, did I make a mistake? Sorry, I copied it. Well, we worked through plus 6x, so we can just continue with plus 6x. My mistake. Let's see, how well does that work out? Okay, so that means we can rewrite our integral as, well, the fraction becomes, let's see, x squared plus 6x plus 30 plus 116 over x minus 4. Where, 116 is just the remainder of the division we used. And now this integral is much easier to do. So integral of x squared is 1/3 x cubed plus 6 divided by 2, 3x squared plus 30x plus 116 natural log of x minus 4. So it makes sense. This is just an example of how we'd apply this method to doing an integral. All right, cool. Let's see. Okay, so next we can move on to partial fraction decomposition. So previously, if doing long division on integrals was a way to solve, problems where we have higher degree on top, lower degree on the bottom, partial fraction decomposition is a way to solve sort of the reciprocal of that, when you have a lower degree on top, higher degree on the bottom. So let me just say that partial fraction decomposition, it's a process to break apart polynomial fractions, so something like p of x over q of x, polynomial divided by another. Actually, let's say and the requirements to use it are that the denominator must have higher degree and the denominator must be factorable and completely factorized. And all that means is I can factor my denominator, it's factorable, and when I start the process, I must already have it fully factorized. So this is a good size. Can everyone still see this? And we start a new page with the example. So example, and just like last time, I'm going to interweave the requirements or the process with the example. So let's say the example we're using is x squared plus 2x plus 3 over x minus 6 plus 4. Okay, so step 1. Let's see, we're going to set the entire fraction equal to the sum of variable numerators over each denominator factor. And I'm doing this with the example. This is a bit hard to explain, but you can imagine plus 4. Imagine that I essentially make a fraction for each denominator factor that I have. So one fraction gets x minus 6, and then the other fraction gets x squared plus 4. The numerators are going to be variables, but the way I assign them is I have to, so I'll even say, the way I'm constructing these numerators is I'm just making a generic polynomial with degree 1 less than what's on the denominator. So for example, x minus 6, what's the degree of that polynomial? It's degree 1. So 1 less than that is a degree 0 polynomial, a constant. So for variable, I can just put a, some constant. What about x squared plus 4? What's that degree? 2. So 1 less than that's a degree 1. So a generic degree 1 polynomial will be something like ex plus c. It's important that we don't reuse variable names here, so you can just kind of go down the alphabet. So after that, now we have to re-add these two together and solve for the numerator. So I'll keep that over there. But if I were to add these two fractions together, in order to add fractions, their denominators have to be the same. So I'm just going to equalize their denominators by multiplying each one, top and bottom, by the other one. And if we solve that out, distribute a over, we get ax squared plus 4a. And if I FOIL this one out, this becomes plus bx squared plus cx minus 6bx minus 6c. And again, this all equals our original. Okay, good. So one thing we can do to make this, a bit easier to solve is that when I have two fractions that are equal to each other with the same denominator, what can I say about their numerators? They also have to be equal, right? So that means you can even also think about it as multiplying both sides by the denominator, but either way, I can set these two tops equal to each other. Okay, from here. If you notice, I grouped all the terms that have equivalent degrees with each other. If we do that, what we can do is, if these both have x squared, I can factor x squared out, right? So this whole term can become a plus b x squared. Similarly, this can become c minus 6b times x. And this is just the constant term, 4a minus 6c. Right? Notice how this side of the equation is also written like, a polynomial. In the same way we've just formatted this one, right? It has an x squared term, both sides, an x term, both sides, and a constant term, both sides. Yeah. So what we can do with that is, the number of x squared terms on this side of the equation has to equal the number of x squared terms on this side of the equation. So that means, if I think of this guy's coefficient as 1, I can set this coefficient equal to that coefficient. So I can say a plus b equals 1. And the same goes for the others, right? This coefficient is 2 for the x, so I can set this coefficient to the x, or 4x, equal to it. And then I can also set constants equal to constants. And And from there, it's just a system of equation problems, right? We have 3 variables, 3 equations. Oh, before we get on to that, did that last process make sense? Like the, we're okay with that, like logically? Okay, cool. So, I mean, yeah, so now it's just a system of equation problems, right? So, I don't know, for example, if we wanted to solve out, I don't know, if we wanted to solve B first, let's say we try to solve B first. So then I would, get A here to get rid of it, and I would get C here to get rid of that. So then this equation will become 4, 1 minus B, minus 6, minus 6, 2 plus 6, B, equals 3. Yeah, sorry about the missing C there. Right, so it's 6C. So it's negative 8 minus 40B equals 3. So therefore, negative 40B has to equal 11. Equals negative 11 over 40. And then, now we can solve for A and C. So A can become, let's see, 1 is the same thing as 40 over 40. So that minus, so we can see A will have to be 51 over 40. Let's see, equal. Okay, so far so good. So if we go back, we can say that our original, our original polynomial fraction has to equal, let's see, A over x minus 6, but we know that A has to be 51 over 40. Plus bx plus c over x squared plus 4, but we know that b is negative 11 over 40. So negative 11 over 40x, and I believe c was 7 over 20, 7 over 20. Wait, what?
So this.
Oh, sorry. All right, all good. And so this technique has a couple different applications when we're integrating. So just go straight to an example here. Okay, so first thing we should ask ourselves, is this a viable fraction to do, partial fractions on? Where if we go back to the requirements, we need to have a denominator with a higher power and a denominator that's factorable. So does that apply in this instance? No. So what we can do is, if I factor out an x if I factor out an x from this fraction, what does the numerator become? 6x minus 3, right? Now, does what I have in here, is that viable for partial fractions? Right, it should be now, because now the numerator's power is lower than the denominator's. Minus 3. And the last thing we need to check is, we need to factor, side note, factor x squared plus 2x minus 8. Which, let's see, what does this factor into? Does anyone know the factors of this integral? Does anyone know the factors of this polynomial?
X minus 4 and x plus 2.
I believe it'd be plus 4. Right, okay, so 4 2 dx. Cool, so now we have a fraction that we can do partial fractions on. So I'm going to say, let remember, we always let it equal some variable polynomial over one factor plus some variable polynomial over the other factors. And again, since these bottom polynomials, they're both degree 1, the top should be degree, right, degree 0. one less. And so if that's the case, then we have which, let's see, if we factor this into there, that'll become ax minus 2a, and this will become bx plus 4b all over the same denominator. Is equal to that. So then we can say 6x minus 3 is equal to ax plus bx minus 2a plus 4b And if I collect all these, let's see, x terms together, and factor, I get that, and then the constant terms become, well, they just are what they are. So I can set this coefficient, the x term, equal to that coefficient with the x term. So a plus b should equal 6, and negative 2a plus 4b has to equal negative 3. From there, so let's say a equals 6 minus b. So then we have negative 2 times 6 minus b plus 4b equals negative 3. Let's do some simplification steps. That's good. Right, so we should be getting b equals 3 halves, and therefore a is equal to, let's see, 6 is 12 halves minus 3 halves of b, so that'll give us 12 minus 3 is 9, so 9 halves. That's right here. So we go back to our integral. What we can say is that our integral is equal to x times, right, a plus 4, a over x plus 4 plus b over x minus 2. right? Because this and this are equal. Where A is 9/2, yeah, A is 9/2, B is 3/2. So 9/2 over x plus 4. And nice thing about integrals, I can always break them into separate ones if I have an addition sign. X. Okay, cool. So how would you guys approach solving this first integral right here? X over x plus 4. I think it's a good idea. Or which should you be? So if we du is going to be equal to, try to write a little bigger, sorry. Right, dx. So this one becomes 9/2 integral of x over u du. And then how do I get the top x in terms of u? Right, if we go back to this equation right here, you can even rearrange it to see that x is, bring the 4 over. X is always u minus 4. And we get integral u minus 4 over u du. Which, again, if I break up the numerator along the addition sign, we can see that it becomes u over u, 1, minus 4 times 1 over u du. So what's integral of 1? Which is going to be u minus 9/2 times 4. And then integral of 1 over u will be natural log of u. And then, we can go back up and do this one as well. So it's going to be really similar patterns. If I say w is equal to, right, denominator, x minus 2, dw would be equal to dx. So I have 3/2 integral of w plus 2 over w. And again, integral of 1 w, integral of 1 over w is natural log w. And we bring them together to get, let's see, 9/2, u is equal to x plus 4, minus, let's see, 9/2 times 4 should be 18. Natural log of x plus 4, plus 3/2, w is x minus 2, plus, let's see, 3/2 times 2 is just 3, natural log of x minus 2, plus 8. Okay, we got it? Any like questions or? Is the handwriting too small? Can everyone see? Okay, we all good for next example? All right. Let's see, what time is it? Just 10:53. Okay. Let's finish on reduction of Let's finish our reduction of trig powers, and if we have any time left over, we can just go over like examples you guys want to go over. Okay, so this isn't really like a really formal method per se. What this is just like. Let's write bigger. This is generally something they go over, just like how to do integrals where you have trigs to like powers higher than 2, so like 3, 4, 5, etc. So. And the most common example you'll see are usually in the form of sine to some power n, cosine to some other power. And I kind of like to break them down into cases, because we do each one a slightly different way. So case 1, I'm going to say both powers are even. So for example, we might have integral of is that too much? Actually, well, just show that it works. Let's do it with 3x. Sine to the fourth of 3x. Right, in this example, cosine is raised to the 0 power, which does count as even. So in cases like these, does anyone know how you would approach seeing something like this, like sine to some high even power? The general method is going to we're going to use the half angle formulas to reduce powers. Where, just as a reminder, what are the two half angle formulas?
1/2 times 1 minus cosine.
Say that one more time.
So it's 1/2 times parentheses 1 minus cosine.
Oh. Equals. Okay, that one is sine squared. So sine squared of x, yeah, like you said, 1/2 1 minus cosine 2x. And cosine is, same, but plus cosine 2x. So in our example, if I have sine to this large even power, what I can do is bring out all the other powers until what's left on the inside is just squared. So in this example, if I want a square on the inside, I have to bring out 2 powers. And using our formula, what is sine squared of 3x equal to? Well, if we use the power reduction formula, it should be 1/2 1 minus cosine of, you can imagine this as twice the original coefficient. So this will be cosine of twice 3, 6. Right. And that's all that squared. So now we essentially have, we can even, let's pull out the 1/2 just to make it clearer. So 1/2 squared becomes 1/4. So here we do algebra. How do we FOIL, it's like, or if we're going to FOIL, if we're going to FOIL out one minus cosine of 6x, let's see, 1 minus cosine of 6x, minus cosine 6x. Let's see, this and this make what? Cosine squared of 6x. So our integral becomes 1/4 cosine squared of 6x. Let's see, this and this minus 2 cosine 6x plus 1. So we can see that, out of these three integrals, right, this, and this, 1 and -2 cosine of 6x aren't too hard. This one should know by heart, and then this one is like, you can either see it or do one u substitution with u equals 6x, but this is not a very difficult integral. How can we fix cosine squared of 6x? Right, we have to apply it again. So this time, cosine squared of 6x becomes 1/2 1 plus cosine of, in this case, what's double 6? That should be 12. So in this formula, it becomes 12x. And now we should be able to do these integrals by hand. What's integral of 1/2? That's 1/2 x. Integral of, so we have 1/2 times, integral of cosine is always going to be what? Positive sine. So in this case, it'll be always divided by the interior, coefficient, sine of 12x minus 2 times 6 sine of 6x plus x. And I guess if we just want to simplify the algebra a bit, that becomes 1/2 x plus 1 over 24 sine 12x minus 1/3 sine 6x plus x. Let's see. Time of 10 minutes. Okay, we got that? And I'm free to, you can take pictures of any of the slides after we wrap up. Actually, let's keep it on the same slide, just because it's so much further down. Okay, different slide. We're just doing power reduction. We're just continuing it. So in the previous case was both are even powers. In this case, let's say whatever. Let's say we're dealing with an integral where both powers of sine and cosine are odd. If that's case, the method we're going to use is we're going to use u substitution. So I'll say u sub where u equals sine or cosine. You can use either. So in this example, that kind of demonstrates the starting point. So I could say here, u is equal to sine. And if u is sine, what will du have to be? Yeah, if u is sine, d will be cosine, right? Sine's derivative. So we have, let's see, sine cubed, so we can, sine cubed can become u cubed, and then we have cosine cubed of x times 1 over cosine of x du. So here we kind of run into a problem in that it's no longer in terms of sine anymore, but how can I change cosine into terms of sine?
Sine squared plus cosine squared equals 1.
Right, so therefore cosine squared is going to equal, what, 1 minus sine squared. So up top I'm going to say, after you use u sub, right, so here we have u cubed 1 minus, since sine is u, this is just u squared. And from there, that's a pretty simple integral, right? This distributes out into u cubed minus u to the 5th. And then that integral will be, what? 1/4 u to the 4th minus 1/6 u to the 6th. All right, and this will have to be our last example, but the final case is, right, before we had even, odd, even, what if we have, sorry, we had even, odd, odd, so what if we have in even, is odd. I guess. And so to solve this one, we're going to use u sub with u is always equal to trig function to the even power. So here, if we use that in our scenario, since cosine is the even power, we can say let u equal cosine of x. Then du will have to be negative sine of x. And our integral will become, let's see, u to the fourth times actually, I guess, right, -1, I can pull it out. But we can see here that sine cubed divided by sine will be right, sine squared which, if you remember the previous problem, we get rid of the sine squared in the exact same way. We replace it with its cosine squared equivalent, and there we can substitute u in. All right, so that covers all the material that you should have gone over this week. Are there any remaining questions or like any big topics that were covered in class that you didn't think I really touched on?
I have a question about this problem.
Oh yeah.
So, would it be possible to do cosine squared squared first and then like substitute in that identity?
Cosine squared squared.
Yeah, and then do like 1 minus sine squared squared and then take it from
And then so then everything will be in terms of sine powers.
there. Yeah, and then do like u equals sine of x.
But the problem is if you do u equals sine of x, what does du have to So that's actually a good idea, but you do have to like sort of save one cosine in order to cancel out.
So if n is odd, n is even, do you just still set the trig function to the even power?
Oh, maybe that's not the best language. I really just mean to say that if one is odd and the other is even. I'm sorry, yeah, because it will apply either way. All right, cool. Any other questions?
Is this going to be similar to doing the cosecant one in tangent?
Yeah, we can do it. Do you want to do a quick example of one of those? Okay, yeah, real quick. So say like tangent. So these types of integrals. Let's see, where are those most doable? It should be most doable when we have these end up being most doable when you have like tangent times secant, when secant is raised to some even power. The reason why is, like, let's say for example we have tan to the 9th secant to the 4th x dx. The way these work out generally is that we're going to let u equal tangent of theta, or x, sorry. Because what does du have to equal then? Right, the derivative of tangent. X dx, so then our integral becomes, so we have u to the 9th times secant 4th of x, 1 over secant squared of x, du, u to the 9th. Oh, make sure you sign out before you go.
Okay.
Times, so secant to the 4th divided by secant squared is secant squared of x. And if this was like 6 or 7 or 6 or 8 or 10, it would just be some other like even power, right? Here just happens to be 2. Or du. And now, if you remember, in the other problems, when we had like an extra sine squared or cosine squared left over, we used the formula sine squared plus cosine squared equals 1. What formula can I use to get rid of secant squared? Or maybe not get rid, but what formula puts secant squared in terms of tangent squared?
Tangent. Or plus.
Plus, right? Secant squared of x equals 1 plus tangent squared of x. So here we have u to the 9th, and then times 1 plus tan squared of x dx. And you guys can solve this from here, but tangent is obviously what u is equal to, so we have 1 plus u squared, du. And then from there, that's pretty solvable. So that's generally the precondition you want. Tangent can be to any power, but secant has to be to some even power. It gets more complicated if secant's to an odd power. I didn't see that in the lecture notes. I don't believe that was covered.
So if we do get one of these problems, it'd be only to the even power.
I'm just going off the notes you guys got. If I see it in the future, I'll make sure to go over it. I'm sorry, I probably would have gone over it too. We just had to get through a lot.
So we shouldn't have actually seen anything with secant. Like secant is the first power with tangent and not like problems or anything.
I mean, all I can say is it was not in the notes that were provided. And I didn't see it like when I help people in the lab with the homeworks. If it's there, I can send out an email if I like see an example of it. But I didn't see one, and it's just a slightly more involved process. I actually have to use integration by parts. But I can make a note to cover that next week if you guys. That'd be good. I'll make a note of that.